This is the first video in BC Calculus on improper integrals, which is section 8.4 in our textbook. And I'm going to do the best I can with my new screenwriting tool to write on this and fill out these notes for you as we go. So I apologize in advance for my handwriting. So what we want to look at first is situations where graphs may look like they have an infinite amount of area under their curve, when in fact the area does converge to a certain amount. So here, for example, we're looking at the graph of 1 over x squared. Now it looks like if I was to start, say, at x equals 1 and to continue to add area underneath that curve, even though the curve is decreasing, it looks like I'm continuing to add amounts of area underneath it, which is true, but the amount of area that you're adding underneath there becomes so much smaller that it really does start to converge to a particular value. But before we really get to that concept, we just want to think about how to integrate it, starting at x equals 1 to some location of x equals b. And you can see on the graph there that they've drawn for us a random, whoops, what is going on? Oh, a random b location for us to kind of look at there. So over here on the right, we have the integral from 1 to b of dx over x squared. So I'm just going to kind of go through this in baby steps. So this would be equivalent to the integral from 1 to b of x to the negative 2 dx. And then as we integrate that, x to the negative 2 would integrate back to negative x to the negative 1, or negative 1 over x, from 1 to b. So that would be negative 1 over b minus negative 1 over 1, so that would become a plus 1. So your answer would be negative 1 over b plus 1. Now what if, though, we were looking at that as b began to approach infinity, as we moved farther and farther to the right underneath that 1 over x squared curve? Well, if we do that, let me scroll up a little bit. If we do that, then the integral looks like the integral from 1 to infinity instead of the integral from 1 to b. Now we can't actually take a limit or an integral to infinity like that because infinity cannot be reached. So what we have to do instead is we have to treat it as the limit as b goes to infinity of the integral from 1 to b of dx over x squared. Now we already know what the integral from 1 to b is because we did it up there above. So this would be the limit as b goes to infinity of negative 1 over b plus 1. So then we're not really evaluating the limit of an integral anymore. We're evaluating the limit of the expression negative 1 over b plus 1. So you actually work the entire integral out, ignoring the infinity concept and just treating that as the variable b. Then once we have our expression, we want to try to evaluate the limit for that. That limit would then be negative 1 over infinity when we substitute the infinity in place of the b. And so then you have negative 1 over infinity plus 1. Well, negative 1 over infinity is just 0. So our final answer is 1. So what that means is that if I continue to try to accumulate this area under this curve all the way out to infinity, that sum would converge to a value of 1. So here we have definitions of improper integrals with infinite integration limits. So you have different types of situations that would be considered improper integrals. If either one of the boundaries of your integral is infinity or negative infinity, then that's an improper integral. And so that would be scenario 1 or scenario 2, where you've got an infinity or a negative infinity. And those could be on either end of your integral. Both of those have to be written in terms of a limit. Usually we say as b goes to, but you can really use any variable you want to, a, b, c, whatever. The third scenario is, what if both endpoints are negative infinity to positive infinity? Well, if that's the case, then you actually have to split it up into two integrals, one that starts at negative infinity and goes to some value of c. Now, c is actually going to be a number, and you can choose whatever you want that number to be. And then your second integral is going to pick up at that c value that you've chosen and then ends at infinity. That's because we can't do an improper integral that has two different improper limits on it. So we split them up into negative infinity to something, and then that same place to positive infinity. And then we just add those two integrals together after we've evaluated them. So let's look at one that diverges here. So we have the integral from 1 to infinity of dx over x. So you would think that I could just approach it the same way as the one I did before, which is actually what I'm going to do. I'm going to think about this as the limit as b goes to infinity of the integral from 1 to b. There we go. I'm just going to use my finger. Of dx over x. So that's 1 over x. You know that that integrates back to natural log, so this becomes the limit as b goes to infinity of natural log of x from 1 to infinity. So then to evaluate that limit, we would have, not from 1 to infinity, from 1 to b. So then that would be the limit as b goes to infinity of the natural log of b minus the natural log of 1. Now the natural log of 1 is 0, so this is really just the limit as b goes to infinity of the natural log of b. While substituting in what b is approaching, we then get the natural log of infinity. Well, the natural log of infinity is infinity. So that tells us that this area under here, we would actually still continue to add enough. Even though it's a very small incremental amount, it's going to continue to grow enough that we say that the area under the curve would actually be an infinite amount of area. When that's the case, then we say that the integral diverges. So this is similar to what we've been doing with sequences so far. All right, so let's look at another example here. We've got the integral from 0 to infinity of e to the negative x dx. I want you to maybe pause the video at this point and see if you can give this one a try on your own. All right, so I've worked it out entirely there. It's really just a matter of integrating the e to the negative x back to negative e to the negative x, evaluating that from 0 to b. And then you end up with negative e to the negative b plus e to the negative 0. But instead of writing e to the negative b, I wrote it as negative 1 over e to the b. And then e to the 0 is 1, so that becomes a plus 1. Work that out with substituting in b going to infinity, and you get a value of 1 there. All right, so let's give this one a try. So again, I immediately see that infinity there, so I know this is an improper integral, so I'm going to rewrite it as the limit as b goes to infinity of the integral from 0 to b of 1 over x squared plus 1 dx, and hopefully you remember what that is. That is the derivative of inverse tangent, so this becomes the limit as b goes to infinity of inverse tangent of x from 0 to b. So that becomes the limit as b goes to infinity of inverse tangent of b minus inverse tangent of 0. So remember, with inverse tangent, we're finding the angle that has that tangent value. So with inverse tangent of 0, the angle that has a tangent of 0 is 0. So this goes to 0. So we're just left with inverse tangent of b. So now we're trying to evaluate the inverse tangent of infinity. So that's when you're asking yourself, what angle has a tangent value of infinity? That might be kind of hard to answer thinking about the unit circle, because you're not really going to have an answer for that. But if you think about the graph of tangent of x, just to kind of roughly draw it out, it looks like this, but it repeats over and over again. Well, this graph is going to infinity right there as it approaches that first vertical asymptote. So if you can remember where that vertical asymptote occurs, you know what the inverse tangent of infinity is. The inverse tangent of infinity is pi over 2, because that's where that vertical asymptote on the graph of tangent of x occurs. So that means that the answer to this integral is pi over 2. Now, one of the reasons that we just discussed L'Hopital's rule is because L'Hopital's rule can actually be used to evaluate improper integrals, such as the integral from 1 to infinity of 1 minus x times e to the negative x dx. If I'm going to try to integrate this, this is actually going to require integration by parts. So, doesn't that sound fun? Let me scroll down a little bit. So with integration by parts, though, I can make my f function that I'm going to take the derivative of, the 1 minus x. So its derivative would be negative 1 and then 0. And so then my g function that I'm going to integrate is e to the negative x. It would integrate back to negative e to the negative x, which would integrate back to e to the negative x. And then let me switch colors so you can see here. So connect diagonally. Change the signs, and so this is going to equal the limit as b goes to infinity of, so matching that stuff up, I would have 1 minus x times negative e to the negative x, so that would be negative 1 minus x e to the negative x, and then negative 1, or minus negative 1 times e to the negative x, so that would become plus e to the negative x, and that is evaluated from 1 to b. So that would be the limit as b goes to infinity of, instead of writing that as negative times 1 minus x, I'm just going to write that as x minus 1 over e to the x plus 1 over e to the x from 1 to b, which is the limit as b goes to infinity. I'm going to combine this some more since that's a common denominator of e to the x. That would be x minus 1 plus 1, so that would just be an x from 1 to b. Now, if I try to substitute, oh, nope, I do need to actually evaluate it. So I've got the limit as b goes to infinity of b over e to the b minus 1 over e to the 1. So the second fraction is fine, it's 1 over e. The issue is the b over e to the b. If you substitute infinity into that right now, you're going to get infinity over infinity, which is indeterminate. So now is when we would need to apply L'Hopital's rule. Let me scroll down so that we have some space. So that would become the limit as b goes to infinity of the derivative of that guy, so that would become 1 over e to the b, because it's its own derivative, and then this guy we don't need to do anything with because he's fine, so he can just hang along there. Alright, so now when we substitute in, that's just going to be 1 over e to the infinity minus 1 over e. 1 over e to the infinity is 1 over infinity, which is 0. 0 minus 1 over e is an answer of negative 1 over e for the value of that integral. Alright, so that's where we're going to stop the first video after example 4 there, and I will make a second video that covers the remainder of the material.